Hello and welcome to this optional video. In this optional video, we are still in section 2.1. We are going to do two things. First, we are going to justify the formula for the length of a path. And second thing, we'll prove proposition 2.3. Okay, so let us start with the justification of the formula giving the length of a path gamma, why the length is computed as an integral of the modulus of gamma prime. Of course, it's enough to prove this or to justify this where gamma is C1, because if we do this, we can just apply the same thing for each part of the path, okay? So, okay, what is the idea? The idea is to approximate the path by a sequence of polygonal paths, right? Like this. Okay, this is one crude approximation. This is a better approximation. This is even better, okay? So what we are going to do is to compute the length of each straight line segment in red, and then sum all these lengths, and we will going to prove that as the partition becomes finer and finer, the length of the polygonal path converges to this integral. Okay, this is the idea. The idea is not new, actually. This is really basic in calculus. Okay, so this is why integrals are used to compute lengths, areas, and volumes, and so on by approximation. Right? Okay, so let us call a partition of an interval alpha beta of the real line as a finite sequence P of points inside the interval, an increasing sequence starting from the lower end, alpha, so T0 equal alpha, then comes T1 and so on, and the final point of the partition is the second end point, or the final point of the interval, right? And we denote by delta Tk the difference between two consecutive terms of the partition, right? And the norm of the partition is the maximum of these delta Tks, right? So in the process of taking limits, we will let the norm of P tends to 0. Okay, so this means that the partition becomes finer and finer. Okay, you can call this the step size of the partition, if you like. Okay, now if P is a partition of alpha beta, then what is the length of the polygonal line in red? It's the sum of all lengths of consecutive straight line segments. So the length of the straight line segments joining gamma Tk to gamma Tk plus 1 in red is just the modulus of the difference, as you know. So the length of the polygonal path joining or approximating the path, so this is gamma of alpha, this is gamma of beta, okay, is the sum of all these lengths in red, right? And we are going to prove that as the norm of P tends to infinity to 0, SP converges to the integral of gamma prime in modulus, right? This is the idea. Why this is so? Okay, first let us write the difference. Let us use the fundamental theorem of calculus that you already know, because you are assuming that gamma prime is continuous here. So the difference between gamma Tk plus 1 and gamma Tk is just the integral of the derivative. This is the fundamental theorem of calculus, right? And now I do a trick. I add and subtract gamma prime of Tk, right? The first term, gamma T prime Tk is constant, doesn't depend on T, so I can put it outside, and then I am left with the integral from tk to tk plus 1, which is just the difference between the bounds, which is just delta tk. Right? So now just take the difference. Gamma tk plus 1 minus gamma tk minus gamma prime tk delta tk is equal to this integral, right? So when I take the modulus of this difference, from the one hand, is less than the modulus of the integral, right? Because these two are equal, actually. We have equality here, right? Should have put here equality. And the modulus of the integral is less than the integral of the modulus, okay? But on the other hand, if I use the triangle inequality, I call this x and this is y, the modulus of x minus y is bigger than the modulus, or just the absolute value, of the modulus of x minus the modulus of y, right? So I get this inequality. And this is true for all k between 0 and n minus 1. And now I just do a summation, okay? So when I do the summation, what is SP minus this? This is, by the way, I hope you recognize this as the Riemann sum corresponding to the integral, right? So SP is just this sum by definition. This is okay. And I didn't change nothing. So I just do the difference and take modulus, right? And then I put these two sums under the same sign. And I apply the triangle inequality. The modulus of the sum is less than the sum of the moduli, right? And now I use the previous identity, right? Because we already proved that this difference now is less than the integral of the modulus, and just do a summation, right? Now, of course, we are going to show that this quantity can be made arbitrarily small. And this is a consequence of the uniform continuity of gamma prime, because gamma prime is assumed to be continuous, so it's uniformly continuous on any interval alpha beta closed. So if epsilon is given, since gamma prime is uniformly continuous on alpha beta, I can find a positive number delta such that gamma t minus gamma s in modulus is less than epsilon whenever the difference between the arguments is less than delta. Okay, so note that here continuity alone is not enough. We need uniform continuity. Fine. So now if the norm of the partition is less than delta, sorry, this is capital delta, so yeah, it's in the opposite direction. So delta tk, the step size of the partition, is less than the number small delta. So, okay. And so if t is between tk and tk plus 1, so the length of this interval here is less than delta. So the difference between t and tk is less than delta, right? Therefore, the difference between their images is less than epsilon by uniform continuity, right? And now I just, since this is true for all t, I just integrate. I can integrate inequalities. So this is less than epsilon if t is here, is in this interval. And now I can put the epsilon outside the integral and I get the difference between the bounds, which is delta tk. And now I just do the summation. When I do the summation, I can put epsilon outside the summation because it doesn't depend on k. And then I get what? The sum of the step sizes, right? They sum to what? To the length of beta minus alpha, because this is just t1 minus t0 plus t2 minus t1 and so on. So ultimately, after cancellation, we get just tn minus t0, which is just beta minus alpha, right? So this, and since epsilon was arbitrary, right? What did I prove? I proved that for every epsilon positive, there exists a constant, a positive number delta, such that if the norm of the partition is less than delta, then the difference between the length of the polygonal path and the Riemann sum is arbitrarily small, is less than beta minus alpha epsilon. So this precisely means, since epsilon was arbitrary, that the difference tends to 0, because it can be made arbitrarily small, as the norm of the partition tends to 0. And we are almost done. because this sum is a Riemann sum actually of the integral. So by definition, actually, it converges to the integral, right, of the modulus of gamma prime as the norm of the partition tends to 0, right? And that's it. Therefore, as p tends to this integral as the norm of p tends to 0, right? And this gives the justification why where does this formula comes from? It comes from an approximation of the path by a sequence of polygonal paths whose step size tends to 0, right? Okay, so this concludes the first point. Second point is a rigorous proof of proposition 2.3, because a student asked me to check his proofs, and actually it was correct, but let me give it here. So I want to prove that the integral of the composition of two paths is the sum of the integrals over each path, right? So as usual, let us start with the easy case where gamma 1 and gamma 2 are not just piecewise but smooth, right? Because we understand better what happens here, because all the ideas are there. Okay, so let us start with this case. Suppose that gamma 1 and gamma 2 are C1, okay? In this case, the composition is piecewise smooth with respect to the partition 0, 1/2, 1, which means what? Which means that gamma is C1 on 0, 1/2 and C1 on 1/2, 1. Okay, but it need not be differentiable at 1/2, right? And therefore, by definition, the integral over gamma is the sum of the two integrals where on each interval where gamma prime is continuous. So it's the sum of these two integrals. Now, since gamma is the composition of gamma 1 and gamma 2, then by construction, gamma t is equal to gamma 1 of 2t, right? And gamma prime is just, I have to multiply by the chain rule, gamma prime of t is gamma 1 prime 2t times 2, right? By the chain rule. And if t is between 1/2 and 1, gamma of t equal gamma 2 of 2t minus 1. And the derivative is, by the chain rule, gives me something similar, right? And now I do in the first integral the change of variables s equal to t, so that ds equal to dt, and the integral becomes from 0 to 1. And in the second integral, I do the change of variables s equal to t minus 1, right? And now I recognize that the first integral, because I assume that gamma is C1, is just the integral over gamma 1. And the second integral is the integral over gamma 2. And that's it. Okay? So all the ideas are there. Now, in the more general case where gamma 1 is piecewise smooth and gamma 2 is piecewise smooth, we proceed as follows. Okay. So suppose that gamma 1 is piecewise smooth on the partition T0, T1, Tn. What does it mean? It means that T0 equals 0, T1 is strictly bigger, and Tn equal 1, right? First thing. And second thing, on each interval tk plus 1, gamma 1 is C1, right? And same thing for gamma 2. Now, of course, these two are partitions of the interval 0, 1. What I'm going to do is to paste together these two partitions after a suitable change of variables. So if T0, T1, Tn is a partition of 0, 1, when I divide by 2, I get what? T0 over 2, T1 over 2, up to Tn over 2 is a partition of 0, 1/2, right? Because I start with the 0, then T1 over 2, then Tn over 2. Tn equal 1, so it's 1/2. And now, if S0, S1, Sm is a partition of 0, 1, then by the change of variables S plus 1 over 2, I get a partition of 1/2, 1. So, and notice that the two partitions now coincide, they have a common point, which is Tn over 2 or S0 plus 1 over 2. When Tn equal 1, so I get 1/2, S0 equals 0, so I get 1/2. So what I did is just I glued together two partitions of 0, 1 after a suitable change of value. So 1/2 is the point of the partition actually now. I can call this partition alpha 0 up to alpha n plus 1. Okay, because I have what? I have n plus m. So from 0 to 1/2, I have n plus 1 terms. From 1/2 to 1, so as m is 1, so I get 1 plus 1 over 2. So this is 1 actually. So I get n plus 1 and m plus 1, but there's a common point counted twice. So I get n plus m plus 1 plus 1 minus 1. Okay, so I have n plus m minus 1. So I have n plus m plus 1 terms, right? And now gamma is piecewise smooth on this partition, actually, by definition, right? Because by construction. So by definition of the line integral, the integral over gamma of a continuous function f is given by the sum of all these integrals. Now I split my sum into two parts, the sum from 0 to n minus 1 and the sum from n to n plus m minus 1, right? And I replace, when k is between 0 and n minus 1, the alpha k is actually just equal to tk over 2. And on the other sum, actually, we are in the second part of the partition. So the first sum is actually the sum of the integrals from tk over 2 to tk plus 1 over 2 of f of gamma times gamma prime. But now, since we are on 0 1/2, gamma of t is gamma 1 of 2t. So I apply the chain rule again to get this. And similar thing for the other half of the partition, right? And now I do a change of variables as before, as in the particular case. So in the first integral, I do the change of variables s equal to t. In the second integral, I do the change of variables s equal to t minus 1. And now I recognize that the first sum is the first integral over gamma 1 by definition. And the second sum is the integral over gamma 2. Right? So this concludes the technical proof of this lemma 2.3, which is very useful and we use it very much in practice. Okay, so thank you for your attention and see you next week.